Yeah. So I'm very glad to start with Luca, which is a colleague here at the Technical University Munich, and he's going to talk about geometric desingularization of non-autonomous differential equation. Please, Luca.
Thank you, Jacopo, for the kind introduction, and thanks for the opportunity to speak here in your mini symposium as a first speaker. So today I will present some joint work with Christian Kühn, who is also at Technical University of Munich, and it is based on a paper which is not yet published. Let me briefly outline the content of today's presentation. So as a first step, we will shortly have a look at the Blowup method in the case of autonomous equations, and we'll then apply this procedure to non-autonomous equations and see what changes in this different setting. It will turn out that this leads to some infinite dimensional phase space and to delay equations. And on this phase space, we are then able to prove some stable manifold or unstable manifold, vice versa theorem. And as a last point, we will see a little bit what future expectations can be seen from this field and how to proceed as a next steps. So the Blowup method originated originally from the algebraic geometry and was used to desingularize or to resolve the singularities in algebraic variety. Of course, we will not consider something here, but here we'll look at some vector field of now first an autonomous equation, just some generic equation which has a non-hyperbolic equilibrium point. And we will then use the Blowup method to desingularize this non-hyperbolic equilibrium point and turn it into something hyperbolic, which will then be easier to analyze. And for this, we use some Blowup map, which is mapping from some manifold into the R to the N, which is the phase space of our equation. And the special thing that this Blowup map has to satisfy is that it's non-injective onto the equilibrium point. And every one of you knows some easy examples. The most common is just a simple polar coordinate change. And here in this case, for any angle, as long as the radius is equal to 0, we will get mapped to the origin. And another quite helpful map that is often used for the Blowup is such a so-called directional Blowup. And in this case, it is not a circle, which is mapped onto the equilibrium point or to the origin in this case, but the line u equal to 0. Well, under this map phi, we can pull it back and we can pull the vector field f back to the manifold, and this induces then another differential equation. And the pre-image of our equilibrium point on this new equation is a completely fixed set without any dynamics. Let us take, for example, some easy quadratic equation, and using here some directional Blowup map turns it now in some different, again, quadratic equation. Here the origin is, for example, a non-hyperbolic equilibrium point which has completely vanishing derivative. After the mapping of our phi, the equation does not look much better. We still have now not only one equilibrium point, but a whole family along the line u equal to 0, which are still non-hyperbolic. So far we have not gained any benefit from this mapping. Well, but the benefit is that in these new equations, the structure is in such a way that we can divide out common factors. And using this division, we can then pose simpler equations. So, well, why are we even allowed to divide simply by some factor in the equations? Well, it corresponds to a rescaling of time. For this purpose, let us consider some generic trajectory of our equation and take such any positive function, let us call it here z, And using this function z, we define a new time via v of t, which is given by the integral over the inverse of z along the trajectory. This function is monotone and has an inverse, and the inverse satisfies likewise a similar integral identity. And using this mapping W, we can now define a reparameterized version of the trajectories of our equation x prime equal to f of x. And if we reparameterize the solutions of this equation according to this W, we will then get, by the chain rule, a solution of the equation psi prime equals to f of psi times z. So we can, by this reasoning, argue that we can multiply or divide by a factor in equations. So, well, let us apply such a division also to our example. What does happen here? Well, previously we had here more terms in our equations, some common terms. Here, the first one we had u squared, and the second one we had 3uv, so a common u, which can be divided out. And now the equation on the invariant set u equal to 0 has two equilibrium points, which in our case now are hyperbolic and not non-hyperbolic anymore. And these hyperbolic points are now easy to analyze using linear methods. Blowing down, meaning reverting the coordinate transformation using phi, we can then get information about the dynamics in the original system. So not in the UV coordinates, but back in the XY coordinates. This picture here simply shows you how this blow up is defined and what it really makes. So we see below is would be the phase space in the XY coordinates, and the blow up mapping from, say here, the circle times some interval. It maps the whole circle onto the equilibrium point. And one also sees that these directional blowups, which are where lines get mapped to the origin, are strongly connected to the polar blowup with a circle, as they are mainly directly the projections onto each of the sides. So you can just view that as charts of the circle as a manifold. The benefit of these directional blowups is that they are easier to compute with and don't rely on trigonometric terms. So far the milestones in analyzing vector fields using the blowup methods are usually of the form that one can show that a finite amount of repeated blowups is able to completely desingularize some non-hyperbolic points. And in dimension 2, this was shown by Freddy Dumetier in 1977. And now quite recently, it was extended into dimension 3. And the aim of our work is to somehow find something which lies in between these two cases, namely something which is more than dimension 2, but a little less than dimension 3. And we will consider two-dimensional equations, which are additional non-autonomous dependency. So, okay, let us move on to the non-autonomous case. And the equation that we will consider is assumed to have such a form. And in fact, we even assume that our function h is exponentially decaying towards the ends, meaning that our function is not only non-autonomous, but it is asymptotically autonomous. And well, we again assume that we have some equilibrium point for simplicity at the origin for all times t. And what we now assume is that we still have some form of non-hyperbolicity, meaning that the Lyapunov spectrum of the origin contains 0. And since the equations are in the asymptotic limit autonomous, the Lyapunov spectrum is just given by the real parts of the eigenvalues of the linearization of f, meaning that we suppose that the f of 0 is non-hyperbolic. Okay, so now let us again apply some directional blow-up and some time rescaling of the form that we want to divide out factors of u, and kappa here is just some exponent that we will need to divide out enough powers of u. So in the previous example, for example, this would be 1, as we needed to divide out 1 power of u. Well, what that does with our equation, so the two functions, big F and big G, that we had before are now turned into some other functions, little f and little g, which might completely depend on the structure of the equations. And the important thing is that our forcing h is now really different, because it is the time that was forcing the little h now is transformed using the complete time reparametrization, which depends on the trajectory. And the functions f and g can be should be chosen in such a way that they, after this rescaling procedure, are now hyperbolic, meaning that the derivative of f is now a hyperbolic matrix. And well, the special structure of this new equation is a delay equation, because at any time point t, the whole trajectory from time 0 until time t makes the forcing. Well, and going out from this equation, it is clear that we cannot only work in the two-dimensional as a phase space, the two-dimensional plane, but have to move into infinite dimensions. We will use, as usual for such delay equations, we will use a segment notation and just denote shifted back to functions defined on the negative real line, which will state the history of our trajectories. And the phase space will be then composed of such functions. And now we suppose two properties. First, we want them to be Lipschitz continuous with some given constant. The reason for that is that the integral inside the function h, since we are dividing by u, so whenever u becomes 0, this can be a singular integral, and using the Lipschitz continuity of the segments, we can assure that this integral exists in the extended sense. So it might be plus infinity. Well, and additionally, we assume that we have some exponential bound on this function. So what does that help us? So one can show that this vector field has some continuously differentiable extension onto all those functions where the u vanishes at some point, because a priori this equation, the right-hand side of this equation, is only defined for all the segments where u is strictly bigger than 0. So whenever u becomes 0, this is not well defined so far, but one can show that it is extendable, and in fact even continuously differentiable, has a continuously differentiable extension. And this means we can now use some linear theory to analyze this system. So, well, and in fact, it turns out that the linearization is given more or less by the derivative of our function f at the origin, and it is independent of the time. So it is the linearization is again autonomous. And on the phase space of segments of history functions, one again can then define a solution operator of the linear equation, which is composing of shifting of the history function and a solution. And note that this solution of operator is only defined in forward time. As we can see also here, solutions of the equation are only defined in forward time. Because otherwise, because we rely on the backwards history of these functions. Well, we assumed that the matrix DF was hyperbolic, so there is some decomposition of the two-dimensional space into stable and unstable eigenspaces. And according to this decomposition, we can also find a decomposition of our phase space B of history functions. And it turns out that on the unstable eigenspace, we are able to extend this, to extend the linear solution operator, not only for forward time, but we can also extend it to negative times. And on these spaces, the solution operator, so the projections of the solution operators on each, so the restriction, not the projection, the restriction onto each of the spaces is exponentially decaying in forward time for a stable one and decaying in backward time for the unstable space. Well, let us now assume that the unstable eigenspace is given by the invariant set that was formed by u equal to 0. And meaning that when that is the unstable eigenspace, we want a stable manifold, this will be transversal to the set u equal to 0. And well, in the following, we just take this xt as the segment that is evolving, outgoing from some initial condition sigma phi. And we were able to show the following theorem. So the stable manifold is formed by all those functions which, when projected onto the stable space, are bounded and are also bounded for all forward times. So it's just the classical definition of a stable manifold. And this manifold is again given as the graph of some function. And it shares the usual properties of a stable manifold. So it is continuous. We, in fact, even continuously differentiable at 0, tangent to the stable eigenspace. It is locally positively invariant, and it satisfies an exponential estimate. So on this stable manifolds, initial conditions decay exponentially towards 0. They are not only bounded, but decay exponentially. How did we prove this theorem? As often, we use the Lyapunov-Perron method. To this end, we first needed to find an appropriate way to define even this operator. Therefore, we introduced some auxiliary function. And with this function, one is able to show the variation of constants formula for in the phase space B. So in the space of history functions, which is very similar to the normal variation of constants formula, but includes here the auxiliary function gamma and a limit. Well, and then using this variation of constants formula, it's quite straightforward to define the Lyapunov-Perron operators. We will work again on exponentially bounded spaces with a norm that is exponentially weighted and depending on sigma. And as I have mentioned before, our vector field can be decomposed into a linear part plus some nonlinear rest term, which vanishes at 0, and also the derivative of r vanishes at 0. And using this rest, we can then define the Lyapunov-Perron operator in the classical sense, again, including the limit of the gamma in appropriate ways. Well, one is then able to show that the Lyapunov-Poron operator is a well-defined self-mapping and a contraction. So we can apply the contraction mapping theorem to find fixed points, meaning, and these fixed points then correspond to bounded solutions. One specialty is that we skip for the differentiability, we do not rely on the contraction mapping theorem again, but we apply the implicit function theorem to a slightly modified operator, which is given by the identity minus f. And applying the implicit function theorem onto that function, we can show differentiability of our function at 0. We cannot directly use such an ansatz for the whole manifold, since it is hard in the non-autonomous case to find uniform, so time uniform estimates of the neighborhood, which is a benefit of the contraction mapping theory. So, and by these methods, we were then able to show the existence of a stable manifold. Well, so what does that help us? The stable manifold in the extended phase space reduces to invariant manifolds in the UV space if we just by appropriately evaluating the segments at the endpoint, so the segments that correspond to solutions, and reverting the coordinates, we get invariant manifolds in our original XY spaces. However, note at that point, since we are reverting also the time reparametrization, the exponential decay of the solutions can no longer be sustained, because when we change the time, this exponential decay will also change the speed. And by reverting the order of the time in our original equation, so looking everything backwards and also performing the Blowup backwards, one can find, using the exact procedure, an unstable manifold, or a manifold that corresponds to an unstable manifold. Well, that was so far what has been achieved. And let me briefly give an outlook on what can be done in the future. So, as already pointed out, it is quite usual that we seek not only for one blow-up, but for repeated blow-ups, because usually only one blow-up is not enough to completely make it hyperbolic. So we here assume that it is sufficient to perform one blow-up to get it into a hyperbolic state. But usually there are more than one necessary, and for that reason we will seek to find a series of blow-ups that make it non-hyperbolic, and it is key at that point to find some characteristic value that in some way represents the quality of the vector field and which decreases. And of course, also the structure of our equations can be made more general. So here at that point, we assume to work with asymptotically autonomous equations. And of course, here one can also think of some periodic forcing or different limits in forward and backward time. Of course, the possibilities are vast at this point. Well, and so that is what I wanted to tell you a little bit about this topic, and I'm happy to answer any open questions now.
Okay, so then thank you very much, Luca.